Okay, question 8. A teacher uses water, waves in a ripple tank to demonstrate transverse waves. The frequency of the water is 0.5 hertz. Calculate the number of water waves produced in 5 seconds. So let's see if we remember what frequency. Frequency is the number of waves a second. The number of waves a second. And we know that that is 0.5. So that means there's half a wave every second. So in 5 seconds, we're going to times that by 5, and we're going to have 2.5. The answer, 2.5. The teacher increases the frequency of the water waves. So there's now more waves every second. Describe what happens to the speed and the wavelength of the water waves. So if you could imagine a low frequency wave, and then you have now a high frequency wave, we could immediately tell what's going to happen to the wavelength. The wavelength, the distance of one between neighboring peaks in this case, is now getting less. So the wavelength is now it's reduced. What's happening to the wave speed? Well, if you remember this equation, V is F lambda. The wave speed is the frequency times the wavelength. We've increased the frequency, so this number is getting bigger, but by doing that, the wavelength has decreased. So by increasing the frequency that decreases the wavelength, the wave speed stays the same. So the wave speed stays the same. Okay, it's going through the same medium, the same substance. In this case, it's still water, so the speed of the wave in that situation is going to be the same. Last part, a student tries to describe water waves in the sea. Okay, so it looks like this is what they're saying then. Water waves moves up and down. The water particles move all the way across the surface of the sea. That doesn't sound right to me. This means that the water moves in the direction of the waves. The water moves in the direction. Part of the explanation is incorrect. Okay, that's a relief. Write an improved and correct description about the water waves in the sea. So before we just dive on in, let's think about this here. What do we agree with and what do we disagree with? Water waves moves up and down. So let's just draw ourselves a little diagram here just to kind of think about what's going on. So they're transverse waves. So they have this typical transverse shape. And the water particles are moving up and down, but the wave is moving perpendicular to that. So that, I'm happy with that first sentence. The water particles move all the way across the surface of the sea, so I don't like that at all. This means that the water moves in the direction of the waves. Well, that bit again is incorrect. So let's think about how we can reword this now. So the water waves moves up and down. Okay, yeah, I'm happy with that. Write an improved and correct description. So I'm happy to start with that. Let's say instead of moves up and down, let's make that slightly better, shall we? Let's see, the water, should we say vibrates? You could say oscillates. Oh, hang on a sec, let's think how to oscillate, double L in there. Water vibrates, oscillates up and down. We could say the wave moves across the sea. Now the water particles move all the way. That's the bit we disagree with, isn't it? The water particles. The wave moves across the sea, but the particles move vertically only. And let's add in here a little bit. Let's get this a little bit. Let's improve this. We'll move up and down. Be vertically only, and let's have this magic word in here. We love this when we transverse waves. Perpendicularly to the wave. Really showing off the examiner we know what we're talking about here. This means that the water moves in the direction of the waves. The water doesn't move in the direction of the wave. What does move in the direction of waves? What's the energy? The energy is being traveled. So let's say the energy of the wave travels in the direction of the wave. There we go. Happy with that? Oh, hang on a sec. There's a part B to this question. Oh, nearly overran there. Let's have a look at part B. A student watches a ball game on the school field. A student sees the ball being hit with a bat, but hears the sound a short time after. Okay, so let's just think about this. So here's someone with a bat. They hit a ball, and here's a student we're interested in, and they hear it a short time afterwards. This is because the speed of light is greater than the speed of sound. Okay, right, I see where this question's going. Describe an experiment which measures the speed of sound in air. The speed of sound. Okay, you can put that in bold there. In your answer, describe the measurements, calculations, procedures needs to give accurate and reliable results. Loads of little bits in this question, aren't there? We draw a diagram. I love a good diagram. Diagram is one of your best friends in physics. It always helps you understand. So let's go back to this question, this idea here. So this sound wave is traveling out, and the person's going to see it at the same. Person's going to see it instantaneously. The light travels so fast compared to sound, about 1 million times faster. The light is going to reach them practically instantaneously, but the sound's going to take a little while to travel there. Sound's got a speed of about 330 meters per second. So if they're 100 meters away, so the length of a field, is going to take about a third of a second or so. So that's a noticeable amount of time. So what could we do? Well, we want a way to kind of measure the time it takes that sound to travel. Because if we could find out the time it takes, we could do the speed is distance. So we just need to measure the distance over the time. So if we could time how long it takes to do, we could do something like that. Now, there are a variety of different ways to do this. It does say accurate and reliable results. So to me, that's implying doing something more than once, taking an average. And the best method that I know for this is finding a nice big wall and stand here and clap. The sound wave will go out, reflect, and you can time you can time how long it takes the sound wave to go to the wall and back again. But you say, well, hang on a second, there's going to be a reaction time and all kinds of issues going on there. And yeah, you're perfectly right. And it does specify an accurate and reliable results. So what I think the best way to do is send a sound wave out. When it comes back, when you hear it, clap again. And so it goes out, back, and when you get it back, clap again. And eventually you'll set up a nice rhythm, and you will negate those random errors that will occur, and also any effect of reaction time. And we could do that, say, 10 times. We could clap 10 times and time how long it takes us to clap 10 times. So let's think about what we're going to do. Firstly, it says the measurements, the calculations, the procedures. So let's hit these measurements ideas. Okay, we're going to need to know this distance. Let's call that D. So how are we going to measure that distance? Well, you could use a long tape measure, or better still, you could have one of these clicky wheels on a stick called a trundle wheel. So trundle wheel to measure large distance to wall. We'll call that D. Let's just label this. Always label a diagram wall, and that's a clapping person. Okay, and then let's say clap once. When hear the echo off the wall, then clap again. Okay. We're going to keep repeating this until a rhythm has been formed to reduce the effect of reaction time and random errors. Again, random errors, a nice little phrase we can always put into exams to show a little bit more about what we're doing. Okay, clap again, repeat, keep repeating until the rhythm is set up, and then time, how long it takes. Actually, we haven't said, it says measurements. Let's be a little bit more time, how long it takes. Let's put brackets in there with a stopwatch. Time how long it takes with a stopwatch to clap and receive the echo back. Let's go 10 times. So let's see, have we done that? We've described all the measurements, we've measured the distances, we measured the time, perfect. Okay, let's have a look at the calculations now. So we know that the speed is the distance over the time. Now the distance for this, well, the sound's gone there and back 10 times. So the distance is going to be 20 times whatever the distance there is. Because if we just clapped once, it'd have gone there and back. That's 2 lots of Ds, but we did it 10 times over the time measured. And that will give us a value for the speed of sound. Let's just see if we've done this right. We've talked about the measurements, we've talked about calculations, the procedure, we've written it here. Accurate and reliable results. So we've done it over 10 times to reduce that stopping distance. Is it reliable? Well, maybe you could say you could get another pair. To repeat. Practical to see if it is reproducible. But I think around there, I think that'll be just about enough to get all the marks, I'd have thought. There are other methods. You could use oscilloscopes and microphones and all kinds of things, but I think that is by far the simplest one to do because all you need is a stop clock and a trundle wheel.